So let's just talk briefly about it, and then I'll have to do a practice problem. I don't think I actually printed that out. That's fine. So I'm not sure what chapter this is. I have to look that up. But it's dimensional analysis and modeling. And we're just going to look at a simple rocket to get an idea of why we do this stuff.
Thank you.
So here is a rocket, and we're going to look at drag on the rocket based on the nose cone length and diameter. So the diameter of the cone and the length of the cone. If I plotted drag on the y and length of the cone, how many lines do you think we would have to have on that graph to get the actual drag, like to understand, okay, what is the relationship with diameter, length, and drag?
Quite a few.
Quite a few. What lines would they be based on?
Streamers.
Well, they would be like, this would be your diameter 1.
Right.
This would be diameter 2, diameter 3, and so forth, right? Every line would indicate a new diameter, a new drag, based on the length, okay? Well, this is a very simple case. What we do is we avoid multiple lines or multiple issues, and we do like a ratio or a non-dimensional number L over D, and we have one line. So it replaces with multiple variables, multiple lines with one. It's kind of like a DOE. If you're in DOE, it's kind of like that, design of experiments. You're kind of eliminating all these issues and making it into one line. Okay? And that kind of is the baseline of dimensionless analysis, why we do it. Bottom line. There's a lot of non-dimensional numbers which are useful. The most one you've seen would be Mach number, and that relates your velocity of your plane or whatever over the speed of sound. The one famous one that is used a lot is Reynolds number. Do you remember that equation? Rho V L over mu. Or it's it's VL over your kinematic viscosity. So what this compares is velocity times the length is velocity, is kind of inertia. So it compares inertia forces over viscous forces. Okay? So us being so large, we have a lot of inertia, right? And as we move through air that has a really small viscous force, it's really low density. Therefore, this Reynolds number, if we're moving, is going to be large. If you take a little steel ball and you drop it in oil, that has a large viscous force, because it has a large dynamic viscosity, this will actually be relatively small. Okay, so Reynolds number is used to compare inertia over viscous. And the cool thing is, and they found this with experiments, if you match your Reynolds number to a large scale like airplane to a small scale model, as long as they have the same Reynolds number, that means they have the same inertia over dynamic viscosity ratio, then all the lift, the drag, the moments, they're all going to be the same. It's really cool how that works, and they found this to be accurate. Okay, so a lot of the times, an airplane, they'll scale the model down, and they'll put it in the wind tunnel, and they'll have the same forces. Okay, you have to match the Reynolds number, meaning you either have to increase the speed in the wind tunnel, or decrease it depending on what you're doing, or change your fluid, meaning you change your dynamic viscosity. So in NASA Langley, they have wind tunnels that they can use nitrogen in there, different type of fluid to change your dynamic viscosity to get the same Reynolds number. I mean, these things are massive, they're huge, and they just fill it with that and just shoot it around. It's pretty crazy how they can do that. So I think I have, let me check. Should have a video. Might be in, don't know if it's in this one. Yeah, Langley, I'm pretty sure. Yep. Give me a minute. I gotta remember where I put this. There's a video. Oh, it's after this. 11. Oh no, I did it earlier last year. I'm gonna show you the video. They took a hummingbird, I'm pretty sure it was a hummingbird, and they made it bigger because it's also due to the length, and they can look at the effects because they matched the Reynolds number.
I was watching one where they took a hummingbird and they put it in a wind tunnel.
They took it in a wind tunnel?
Went to a high-speed camera to see how it moved.
That might have been, maybe this is very similar.
They stay hovering.
Oh, right there. Oh. See if this will work. There you go, I zoomed up. So, okay, these are just the wings of a fly. Okay, so we know a fly is really tall, really small wings. Okay, what they did is they made it bigger, and this is like really thick fluid that they're doing, and they're moving these back and forth. And they can look at what the flow patterns are, and they can hook these up to force balances to figure out what kind of forces they're created. I'll just play it one more time so you can see. But again, they match the Reynolds number of a fly going through air, flying their wings. They change the size and they change the working fluid to get the same Reynolds number. I mean, that would be a cool capstone, making that, right? I mean, that would be pretty challenging to do, but we have everything you could do it in the whole machine shop. What else do I have? This is a side view, I think, of it. Take a little bit to load. So now we're just looking at the side profile a little bit better. Quality isn't the greatest. But they wanted to see how the flow patterns were and how they actually work and fly. What's that? I'm not sure what that is actually. No. If you type in RoboFly, you can probably find that out. No, I don't know the working fluid, but it's definitely not air. No, it's like a thicker fluid than air. Not as thick as oil.
I wasn't sure if you could put it in air and like add dust or something.
You would need it to be a continuum, like not a mixture. Yeah, because you really want to make, Because then you would have to figure out your new dynamic viscosity with that. Yep. They've done, I don't know if your homework deals with the RoboTuna. I don't remember, but they've actually built a scaled model of a tuna, but it's a robot tuna, okay? And they can throw that in wherever they want in the ocean and then test everything. It's pretty cool. It's really cool. But let's just do a practice problem. I think it's right here. Is it this one? Yeah.
Understand 370, there's 300 millimeters.
That RoboFly? Yeah. All right. Sorry, I didn't print this off for you. But let's, I will keep this in the notes and we'll write our givens for it. On the right page. Yep. You put that over here and I'll do the givens on the left. Okay. All right, so the student team is to design a human-powered submarine for a design competition. The overall length of the prototype submarine is 2.24 meters, and its student designers hope that it can travel fully submerged through water at 0.52 meters per second. The water is fresh water at 15 degrees C. The design team builds a 1/8 scale model to test in their university's wind tunnel. The shield surrounds the drag balance strut. We'll talk about that in external flow. The air in the wind tunnel is 25 in 1 atmosphere. What is the airspeed do they need to run the wind tunnel in order to achieve similarity being the same type of flow? So what they're doing is, it's kind of weird. They're building a prototype that's going to go in water. But they want to build a model, okay, that goes in the wind tunnel to test, okay, before they go out and test. So let's make some subscripts here. So the prototype is 2.24 meters. Velocity of the prototype, 0.52 meters per second. Temperature of the stuff they're doing is 15 degrees C, which is roughly 288 Kelvin. The temperature of the model is 25 degrees C, which is 298 Kelvin. And the length of the model is 1/8 of the prototype. And what we want to find is the velocity of the tunnel, or the velocity that the model has to go. So if you look at this initially, we're making a smaller model. We're kind of using a completely different viscous force, but in reality, usually if you make something smaller, you have to increase the speed in the tunnel. So the speed should be higher. All right. So let's get right to the solution. So we're going to match Reynolds number. So Reynolds number of the prototype must equal Reynolds number of the model. So rho of the model, velocity of the model, length of the model, over dynamic viscosity of the model. Oh, I should have done prototype first, sorry. I'll do P's first. Rho of the model, velocity of the model, length of the model, dynamic viscosity of the model. And I'll get to here and I'll pause. Velocity of the model, dynamic viscosity, rotate the model, density of the model, so just rearrange that for the velocity of the model. So, how do you find the dynamic viscosity of its temperature? Or, I don't remember, somewhere in the back there. Yeah. You could find the tables, do that. Or there are equations that you can do for gases or for fluids to find it. Okay, I'll just give you the values there in the back. Actually, I think I might have the table number. Do I have the table number? No, I don't. What's the density of water, which is the prototype? 1,000 kilograms per meter cubed. How do you find the density of the air? Sure. What else can you use? What formula? Come on, thermal students. Everyone's had it. Even the new students. They just had it. What does air consist of? Okay. And what can we consider nitrogen as? Yeah. And so it's a gas. The ideal gas equation. There we go. So those two are found in the back of the book. The density of the prototype is 1,000 kilograms per meter cubed. The density of the model. What's that? What is? Oh yeah. Yeah, because we're in water. Yeah. Because they're going to throw it in water. Sorry. I'm confused. So I just use the ideal gas equation, rearrange it. And actually, what is P atmosphere?
101.
Yep. kPa. Or 101.325 pascals, whatever you want. What's the R value for air? 287 joules per kilogram K. And temperature has to be in Kelvin. Always use absolute, unless it's otherwise said not to. I know some statics or strengths equations use Celsius. I remember students showing me that. So, but that, I think it tells you it's in Celsius. But anything else is in Kelvin. Then so far is okay. What do we substitute? I'm going to rewrite this here. We have LP, and what did I tell you LM was?
1/8 over
Yep,
LP.
so it's
And
1/8 LP, and the LP's cancel. See how that works? Because LM is 1/8 of LP, so you just plug that in there. So technically, the 8 goes up on top, right? So just write that down, and then I'll just give you the answer, because you have everything. And when you get it, VM becomes 57 roughly meters per second.